Lighthouse Scientific Education presents a lecture in the Energy series. The topic, Energy and Reactions, Thermochemistry. Material in this lecture relies on an understanding of the previous lectures, temperature, types of reactions, bonding, an overview, and advanced concepts with gases. Material at the end of chemistry courses build on a foundation of earlier material. Energy is a big topic, and we will begin the lecture with some context on different forms of energy. It is also a topic that's been covered to some degree before. A review of heat is given that leads to an examination of chemical reactions from the perspective of an energy diagram. This is a good place to discuss catalysts. The second part of the lecture is given over to thermochemistry. There's an introduction to enthalpy and a comparison of exothermic and endothermic reactions. Also covered is specific heat and heat capacity, with an application using a process called calorimetry. Energy can be a difficult concept because it has no physical form. Historically, the study of energy lagged behind the study of matter due to that absence of physical form. The lack of physicality can be highlighted with a description of the 5 main forms of energy. First up is thermal energy. That is essentially heat, and a topic we will explore more in depth. The form of chemical energy is one we've come across before. A chemical bond can be described by the energy of making or breaking the bond. It takes energy to break bonds. Ionic and covalent bonds are familiar examples. Another form of energy is electromagnetic. Light and electricity are forms of this energy and are usually covered in a physics class. And then there is nuclear energy. It is the energy stored in the nucleus of an atom. It is discussed in the nuclear chemistry series of lectures. Finally, there is mechanical energy. The most common forms are kinetic and potential energy. Kinetic energy is discussed in the Gas Advanced Concepts lecture. This lecture will focus on thermal and chemical energy. Any discussion on energy has to begin with the law of conservation of energy. Energy cannot be created nor destroyed by ordinary means. Energy, however, can be converted from one form to another. The amount of energy, however, has to remain constant. This is very similar to the law of conservation of mass, which says that mass cannot be created or destroyed. These are powerful laws, but there is a loophole. Albert Einstein showed that mass and energy can be converted into each other. That interconversion is summed up in his famous equation E equals mc squared. Energy equals mass times the speed of light squared. To close the loophole, the law of conservation of mass and energy are modified to say that the total amount of mass plus energy is constant. Another way of saying this law is that the change in the amount of mass plus the change in the amount of energy is 0. There is no net increase or decrease in the total amount of mass plus energy. Therefore, if mass is destroyed, it creates energy. And if energy is destroyed, it creates mass. With a nod to Einstein, in this lecture, we will stay in the territory in which the law of conservation of energy holds for all conditions. Energy cannot be created or destroyed. And that goes for the form of energy called heat. The components of heat, atoms and compounds, are in constant motion. This includes those in solid objects. The particles in solids vibrate and jiggle in place. In previous lectures, we saw that motion is energy, and motion energy is heat. Heat is thermal energy, and since it is also motion, it is a form of mechanical energy, another physics-based topic. More motion means more heat. That seems straightforward. And since adding heat is adding motion, it should be expected that most substances will expand when heated. That's mostly true, but not always true. There are instances, like with pure water at particular temperatures, that adding heat actually causes a decrease in volume, most notably when moving from ice to liquid water. As for units, there are two common forms used for thermal energy. The most familiar is the calorie. It is abbreviated CAL. Calories are used to indicate the amount of energy in food. The definition of the calorie is the amount of heat needed to raise the temperature of 1.00 grams of water 1 degree Celsius. The other type of unit is called the joule. It is abbreviated as J. The joule is named after the famous 19th century scientist James Joule. He was able to relate thermal energy to mechanical energy. That was a major discovery. The relationship between calories and joules is 1.00 calories equals 4.184 joules. This relationship can serve as the basis for unit factors that can be used in conversion between units of calories and joules. Staying with heat. Heat is a transfer of thermal energy between two objects that are at different temperatures. Heat always flows from a warmer object to a colder object. Colder is a relative term. It means having less heat than something else. Since heat is motion, this statement implies that motion is transferred from an object that has more motion to an object that has less motion. Importantly, the amount of thermal energy transferred is given the symbol Q. We will make extensive use of Q in the rest of the lecture. Q is almost a stand-in for heat. With motion, there is collision. More heat means more collisions. Collisions involve a transfer of energy, a transfer of motion. This is important because for chemical reactions to occur, particles have to collide. Chemical reactions are going to be a transfer of energy. In the bonding and overview lecture, we introduced the reaction coordinate. It is a common graph or diagram used to compare the change of energy in a chemical reaction. It is a graph based on time. The x-axis is the time axis. It is not like how many seconds have passed, but rather a progression of the reaction, as in before and after the reaction manner. The y-axis is the total energy of the reaction as it proceeds. The reaction coordinate has this general shape. Reading left to right, there is a before platform that marks the energy of all the material that goes into the reaction before the start. Moving to the right on the time axis, we come to the after platform that marks the energy of all the material present after the reaction. The reaction coordinate is a way to visualize the change in energy as a reaction proceeds. Colored spheres are added to the platforms as a demonstration reaction. Two initially separate spheres are combined or bonded together in the reaction. When they are separate, they are considered reactants, and when they are bound, they are considered products. In this reaction coordinate, the before energy of the reactants is higher or greater than the energy of the products. The energy difference between the reactant and product platforms is the energy of the reaction. In this reaction, there is a release of energy in going from the higher energy reactants to the lower energy products. Reactions that release energy are referred to as favorable. Favorable just means that the reaction releases energy and that it is likely to occur. It says nothing about how fast the reaction will occur. Likely could be 1,000,000 years. Another term for a reaction that releases energy is spontaneous. Spontaneous sounds fast, but in this context of chemistry, it only refers to the energy of the reaction being favorable. Spontaneous could be a million years, so it has the potential of being a confusing term. To help give spontaneous some context, consider two forms of carbon: diamonds and graphite, commonly and incorrectly referred to as pencil lead. Going from diamond to graphite has a release of energy, and therefore is a spontaneous reaction. But one should not expect the transition to occur in their lifetime. Favorable energy does not mean favorable time. A feature of the reaction coordinate that does factor in the speed of the reaction is called the activation energy, E sub A. It is the energy difference between the reactant and the top of the graph. It is an additional amount of energy needed to get the reactants to convert to products. There's always a cost to get the reaction moving. The definition of E sub A is the minimum amount of energy needed for a chemical reaction to occur. In many reactions, it reflects the energy of breaking the chemical bonds of the reactants that precedes the formation of new bonds in the products. The higher E sub A, the more energy the reaction needs at the start. That can be thought of as an energy barrier to the reaction. For diamonds to graphite, it is a huge energy barrier. Once the E sub A has been obtained, there is a release of energy. Part of that release is an amount equal to the activation energy. You get back out what you put in. From an energy perspective, this part of the release of energy and the activation energy cancel out. What is left is just the release of energy based on the height of the reactants and products. The take-home lesson with this diagram is that making bonds releases energy. Now consider a reaction in which the energy of the reactants is lower than the energy of the products. This reaction coordinate shows the breaking of a chemical bond in going from reactants to products. The net energy of moving from reactants to products is one of consumption. In the end, the reaction will have to get energy from somewhere in order to proceed. It will also need additional energy to overcome the activation energy barrier. As with the previous diagram, that same amount of energy is returned, leaving the energy difference of the reaction being based solely on the energy of the reactants and products. Reactions that consume energy are referred to as unfavorable and are not likely to occur on their own. The term non-spontaneous is associated with unfavorable. Take-home lesson here is that breaking bonds takes energy. Now, let's keep this reaction coordinate and bring back the first reaction coordinate. These are two versions of the same equation, except they are written in reverse. One is breaking a bond, and the other is making that bond. The important point here is that the energy of breaking the bond is positive and unfavorable, which is the exact opposite of the energy of making that bond. This is an example of the law of conservation of energy. The energy of making and breaking a bond is the same, except that it goes in different directions. One is consumption, positive, and one is release, negative. Bringing back the take-home lessons, we can add energy is conserved. One last concern with the reaction coordinate, and this is best shown with the favorable reaction coordinate. It has to do with the activation energy. It is the energy barrier to the start of the reaction, and on a first pass, it can be said to indicate how slow or fast the reaction moves. Bigger barriers, slow. Smaller barriers, fast. There is a way to reduce the height of the barrier. It is the introduction of a substance called a catalyst. Catalysts increase the rate or speed of the reaction. They speed up a reaction. Reaction rates are covered in the kinetic portion of this series of energy lectures. Importantly, a catalyst is not consumed in the reaction. It participates in the reaction, but in the end, it is returned to its starting state. Consider the reaction of hydrogen and oxygen gas, forming water. This is a favorable reaction, but can be dramatically sped up with the addition of palladium metal. The metal, Pd, is unchanged in the reaction, so does not belong as a reactant. Its presence as a catalyst is included in the reaction equation by placing it above the reaction arrow. The only thing the catalyst does from an energy perspective is to lower the activation energy. It reduces the energy barrier to the reaction. Graphically, it would alter the reaction coordinate like this. The hump is lower, but there will be no change to the energy of the reactants or the products, so there is no change in the energy released. It is still the difference in energy between the products and reactants. If it cannot change the energy of a reaction, it cannot make unfavorable reactions favorable. The reaction coordinate will serve as an aid in describing the various energy features covered in the rest of this lecture and in the next couple lectures. Another set of terminology that needs to be developed is the system. In terms of energy, a system is a collection of matter within a fixed set of boundaries. Those boundaries can be physical, like the sides of a container, or they can be figurative, like a location. The system is not a real thing. It's a conveniently defined area. The person studying the chemistry defines the system. The system is useful in describing a thermodynamic process. It helps us qualify or quantify the flow of energy. Contrast system with the term surrounding. It is everything outside of the system. Any piece of matter is either in the system or it is in the surrounding. As such, the universe is composed of the system and the surroundings. If something is in the universe, it is either in the system or in the surrounding. Like energy, the system is understood from a conceptual perspective. There are 3 types of systems, and we can visualize them using a container, like a flask. What is inside the flask is the system. The thing that distinguishes the different systems is the exchange of energy and matter with the surroundings. The first system is called an open system. It allows an exchange of heat and energy between the system and the surroundings. An open system can also have an exchange of matter with the surroundings. An open flask, sitting on a table, can be warmed or cooled by its surroundings, and can have some of its contents evaporate into the surroundings. Now, what would the difference be if a lid were added to the flask? That would make this a closed system. Closed only refers to the exchange of matter. No matter goes in or out. The closed system is still capable of exchanging heat and energy with the surroundings. But what if our flask, with the lid, is covered by some type of insulation? This would be an isolated system. Nothing gets in, nothing gets out. No exchange of matter, no exchange of energy. In the real world, this type of system is rare. Heat almost always moves between the system and its surroundings. Still, the isolated system is useful in understanding the flow of energy. One last term with systems: the internal energy of a system. It's abbreviated either as capital U or capital E. We will use E, but both are common abbreviations. E is the total energy of the system. For an open and closed system, that E can change. For an isolated system, E cannot change. We will see E a little later in the lecture. On to thermochemistry, and we begin by covering a couple definitions to provide some distinction. Thermochemistry is a branch of chemistry concerned with the study of the exchange of energy or heat in a chemical reaction. Thermo means heat, so it seems fitting that the chemistry of heat is thermochemistry. Compare that to thermodynamics. It is a branch of chemistry concerned with the exchange of energy and work in a system. There is a lot of overlap between these two, but the key term that separates them is work. Thermodynamics and work are topics covered in the next lecture. Important to both branches is enthalpy. It is given the term capital H for short. Its thermodynamic definition is the internal energy of a system plus the product of the pressure and volume. And that is a pretty sophisticated definition. At this level of chemistry, the more useful definitions are the heat transferred under constant pressure and heat content, or total heat. Heat uses the designation of Q. Enthalpy is usually looked at as the difference in enthalpy in a chemical reaction, delta H. Delta means change or difference, with a before value being subtracted from an after value. Delta H in a chemical reaction is equal to the enthalpy of the products after the reaction minus the enthalpy of the reactants before the reaction. This products minus reactant delta equation is a very common format in the study of energy of a chemical reaction. We've already seen it in the change of energy on a reaction coordinate. Almost all reactions will have one or two outcomes with this equation. Delta H is positive or delta H is negative. Each outcome has its own name. First, there is exothermic reaction. It is a process that releases heat from the system into the surrounding. Using this generic chemical equation with small letters being coefficients and capital letters as compounds, exothermic reactions have, as a product, heat. Heat is released. Heat doesn't have to be included in the chemical reaction, but putting it there does show the flow of heat. The change in enthalpy is negative, less than zero, for an exothermic reaction. That is, the enthalpy of reactants is larger than the enthalpy of products. The negative release of energy is heat. As a product, heat is said to be lost to the surroundings. The system lost heat. As an example, when hydrochloric acid is added to water, the reaction produces heat. If the reaction takes place in an open flask, the generated heat will be lost to the surroundings, like the atmosphere or the tabletop. At some point, the flask will return to room temperature. The heat is gone. If, however, the flask was insulated and treated as an isolated system, the heat would stay within the system, and the temperature of the system would increase. It is easy to get confused with whether energy is gained or lost, or delta H is positive or negative. It takes some time to sort these things out. The other option with delta H is the endothermic reaction. It is a process that absorbs heat from the surrounding into the system. For these reactions, heat is more of a reactant. It is required to make the reaction go. The change in enthalpy will reflect that with a value greater than zero. The system gained heat. The products incorporated that heat and have more heat than the reactants. From the perspective of the reaction coordinate, endothermic reactions consume energy. That is why heat is added to make the reaction go. So the heat of the reaction has to be greater than zero. The system gained heat. It has more than it started with. One last point. In an isolated system, where there's no transfer of heat with the surrounding, the temperature of the system decreases. The reaction is pulling heat from the system. Endothermic reactions feel cooler. Those instant cold packs used to treat injuries are driven by endothermic reactions. Okay, let's compare a single reaction in the forward and reverse direction. To keep it simple, we will use the freezing of water, liquid to solid, and the melting of ice, solid to liquid. Same process, different direction. Freezing is an exothermic process. Heat is taken out of the reactant liquid water to get the product of ice. Energy is released. It has long been a practice of farmers to put a bucket of water down in the cellar with their canned goods when the temperature is expected to go below freezing. As the water freezes, it releases heat and releases negative 6.01 kilojoules of energy for each mole of water. The negative sign denotes a release of energy. Where did that number come from? It was looked up in a table. As for melting process, it is an endothermic reaction. To go from ice to liquid water, heat has to be added. Everyone knows it takes heat to melt ice. But how much heat does it take? Try 6.01 kilojoules per mole. Conservation of energy tells us that these energies have to be the same size or the same magnitude. The sign will be different to designate the direction of the flow of energy. On to a new topic: specific heat and heat capacity. This topic is a recognition that not all materials handle the flow of heat the same way. Specific heat is the amount of heat, Q, required to raise 1 gram of a substance by 1 degree Celsius. All materials, be they elements, molecules, or compounds, have their own specific heat. These can be found in a lookup table. Heat capacity, C, is the amount of heat required to raise a unit of mass of a substance by 1 degree Celsius. These two definitions only differ in their quantity of matter. Specific heat only applies to a mass of 1 gram. Heat capacity is dependent on the amount of matter and will be the quantity generally used because it is a broader definition. Another definition that we should cover is also connected to amount: molar heat capacity. It is the amount of heat required to raise 1 mole of a substance by 1 degree Celsius. All very similar definitions, dealing with a substance's capacity to handle heat. Consider adding heat to a substance. There's an expectation that the temperature of that substance will go up. But by how much? What factors influence the change in temperature? Some factors like mass are straightforward. It takes longer to boil a larger pot of water. It takes more heat to get the large amount of water to that same 100 degrees Celsius. Some factors are less obvious. That includes the heat capacity. It is the recognition that different materials require different amounts of heat to raise the temperature to a similar degree. Consider taking food out of the freezer to thaw on the counter. Given enough time, any food will warm up to room temperature. But if an equal amount of ice cream and frozen meat are put out to warm up, they will do so at different rates. The ice cream will melt very fast, whereas the meat will take a longer time. They both get heat from the air, but the meat will require much more heat to warm up to the same temperature, room temperature, because it has a higher heat capacity. The nice thing about energy is that it doesn't require an explanation of how a substance actually handles the heat. It is just concerned with how much heat. Same argument can be made with cooking. Not all foods cook at the same rate. We could put these factors together in a formula that relates the amount of heat with the change in temperature. Add heat, and there's a positive change in temperature. Remove heat, there's a negative change in temperature. The formula will need to have a mass component. More mass needs more heat to warm up. And it will need to have a heat capacity component. That is where the type of material comes into play. And it is found in a lookup table. It has to be provided. The mass can be weighed. And the change in temperature is an experimentally determined value. It is measured. A temperature is taken before the introduction or removal of heat, T initial or Ti, and a temperature is taken after the process, T final or TF. TF minus Ti is delta T. An understanding of heat comes from measured mass and the temperature change. All right, what about units for heat capacity? The lookup table will provide these, but we can reason them out from the formula. The best way to determine units is to isolate the variable of interest on one side of the equation and gather the units from the other side of the equation. That is what equation means. To get C isolated by itself, divide both sides of the formula by its neighbors, M and delta T. That gives this expression. C has to have the same units as Q, joules, over mass, grams, and change of temperature, degrees Celsius. That puts formula and units in shape, so an application is in order. How much heat is needed to raise 20 grams of H2O from 22 to 25 degrees Celsius? This is a new type of problem, so it might look a bit daunting. We could use our general problem-solving technique and get a setup of knowns and unknowns and find a relationship that matches them. But since this is a demonstration of the equation, let's just get the Q equal equation and fill it out using the formula as our guide. We need to find the heat capacity for water. But how? Look it up. These are experimentally determined quantities and can only be gotten from a table. The heat capacity for liquid water is 4.186 joules per gram Celsius. Add that to the formula. The next variable is mass. That is given in the problem as 20 grams. Insert that into the formula. Finally, there is delta T. We will initially add delta T to the formula as a variable because it has an equation all to itself and will need to be solved separately. Does the problem provide TF and TI? It does. But which temperature is associated with which variable? A deeper reading of the problem says that the temperature is raised. It starts at a lower temperature and goes up. The initial temperature is 22 degrees, and the final temperature is 25. TF minus TI is 25 minus 22. The change in temperature is 3 degrees Celsius. Insert that into the equation and solve. Since grams and Celsius are in the denominator of the heat capacity, they cancel out with the grams and Celsius in the mass and delta T. Only units of joules are left, which is consistent with heat. The math has the heat at 251 joules, or using a metric conversion, 0.251 kilojoules. A final topic takes this heat equation to a lab setting. It deals with calorimetry. That is the process of measuring the heat transfer of a chemical reaction or a physical change. Melting is a physical change. There are extremely sophisticated calorimeters, and some that are not so sophisticated. Pictured here is what is called a coffee cup calorimeter. It is a styrofoam cup. Styrofoam is an insulator. It, to a reasonable degree, prevents heat from going into or coming out of a cup. Add a lid, and it is a short-term, isolated system. A common laboratory experiment uses a coffee cup calorimeter and attempts to identify an unknown metal by determining the metal's heat capacity and comparing that experimental measurement to a list of heat capacities of well-known metals. Let's run through an example of the setup. to familiarize ourselves with the process of calorimetry. That kind of experiment begins by adding a known mass of water to the coffee cup, M sub W. A stir bar and a thermometer are considered part of the calorimeter. The system is left alone until it comes to room temperature. The temperature is noted and given the term Ti, W, initial temperature of water. The W specifies water. A hot piece of metal of known temperature and mass is going to be added to the water. It has an initial temperature, Ti, M, M for metal, and that is different from Ti, W. The metal is added to the water, and the cup is sealed, isolated system. Once the metal has submerged, it begins transferring some of its heat to the water, and the water starts to heat up. Eventually, the water and the metal become the same temperature. That is the final temperature, TF of the experiment. No comma W or M is needed because both the water and the metal share this same final temperature. The water heated up and the metal cooled down. Importantly, due to the law of conservation of energy, the amount of heat gained by the water is equal to the amount of heat lost by the metal. A transfer of heat has occurred. We can further explore this with the heat equation. For water, the heat gained is equal to the heat capacity of water times the mass of water in the cup times the increase in temperature due to the transfer. For the unknown metal, the heat lost is equal to the heat capacity of the metal times the mass of the metal times the decrease in temperature due to the transfer. Since the heat gained by the water is equal to the heat lost by the metal, the Q's can be equated. The negative sign on the heat of the metal shows that the heat was lost. As stated earlier, the objective of this particular example is to identify the unknown metal by finding its heat capacity. We can calculate C sub m in this formula by using the values measured in the experiment. That is done by using the equation that equates the Q's and expanding it by using the definition of the Q for water and the definition of Q for the metal. Remember, there's a negative sign in front of the variable representing Q for metal, and that needs to be included with the definition of Q for the metal. Now, to get the heat capacity of the metal, we need to isolate it on one side of the equation. To do this, we divide both sides of the equation by the neighbors of C sub m, M sub m, and delta T sub m, and yes, the negative sign. The resulting expression is rather busy, but it is made up of known terms and measured quantities from the experiment. In practice, it's not as complicated as it looks. And that concludes the material of the lecture. As a recap, energy cannot be created or destroyed by ordinary means. That is the law of conservation of energy. Energy can be converted from one form to another. Motion energy is heat. The unit types for heat include calorie, which is used in biology, and the joule. The energy of a reaction can be shown graphically using our reaction coordinate. Essentially, it is an energy versus time plot of the transition from reactants to products. The reactions that release energy are deemed favorable. They are said to be spontaneous, but that is not an indication of the speed of the reaction. Reactions that consume energy are deemed unfavorable and are said to be non-spontaneous. An important feature of the plot is the activation energy. It is the minimum amount of energy needed for a chemical reaction to occur. It is kind of an energy barrier to the reaction. A catalyst is a substance that increases the rate of a reaction. It is not consumed in the reaction. It only lowers the activation energy. It reduces the energy barrier. A system, in the thermodynamic sense, is a collection of matter within fixed boundaries. Outside the system is the surrounding. There are three types of systems, and they are based on what can transfer between the system and the surroundings. In an open system, matter and energy can exchange. In a closed system, only energy can transfer. And in an isolated system, there is no transferring of energy or matter. An important thermodynamic quantity is enthalpy. Its designation is capital H. The definition of enthalpy is the internal energy of a system plus pressure times volume. Other definitions include heat transferred under constant pressure and heat content or total heat. Like many thermodynamic quantities, it can be expressed as a change in a reaction. The change in the enthalpy of a reaction is the enthalpy of the products minus the enthalpy of the reactants. Endothermic reactions are one that absorbs heat from the surroundings. The heat of the reaction is positive because the products absorb the heat and have a larger enthalpy. Exothermic reactions are one that release heat from the system. The heat of the reaction is negative because the reactants lost some energy to form products. Heat capacity is the amount of heat required to raise a unit of mass of a substance by 1 degree Celsius. Heat capacity varies by substance. Calorimetry is an experimental process of measuring the heat transfer of a chemical reaction or physical change. It makes for an interesting lab period. And that concludes our lecture. Chemical reactions follow the energy.